Well, hello again, mathletes. So this is the second video in our series on antiderivatives and finding them. So we're going to go through a couple of examples and then introduce this idea of an initial value problem. And the initial value problems are the ones where we can actually find the value of c that we're generating when we're finding this indefinite integral. So without further ado, let's go ahead and take a look at our examples. Excuse me. So let's go ahead and start with, let's say I want the indefinite integral of 2x squared plus 3x minus 2 dx. Okay, so what's really nice about this, and it is very similar to when we find derivatives, we can use those linear properties of the integral and actually split this up into three integrals and pull the constants through each one of them. So I can rewrite this as 2 times the integral of x squared dx plus 3 times the integral of x dx minus 2 times the integral dx. Okay, now technically the integral dx is a 1 dx, right? So that probably looks a little bit different. We'll handle that here in a second. Now, looking at this first one, the integral of x squared is going to be x cubed over 3. So this is now 2 times x cubed over 3 plus 3 times the integral of this, which is going to be x squared over 2. And then it's going to be minus 2 times the integral dx. Now, it's the integral of 1 dx. And if we think about it, what has a derivative of 1? Well, it's just x, right? Just the variable x by itself has a derivative of 1. So if you want, you can think of it as 1 dx, but we almost never write the 1 in there. It's just like everything else in math. It's not needed, but it is technically there. So this is negative 2 times x. And then I have to also add a constant there, right? So whatever happens, I still have to add that constant because it's an indefinite integral. Now, just kind of rearranging this a little bit so it looks nicer, this is now 2/3 times x cubed plus 3/2 times x squared minus 2x plus a constant. Right? And so we just found the antiderivative of this. And you notice we just did it term by term. And not only that, we only had to pay attention to the variable part of this. Right? That was actually really nice. Honestly, I would like to see you guys get to the point where you can actually just jump straight from the integral to it straight from the integral to the answer, I suppose, in this case. But yeah, that's our answer for this. Now, let's go ahead and take a look at another one here. Let's say I wanted to take the integral of secant 3x tangent 3x dx. Okay, now if you look at that table of integrals or indefinite integrals that I wrote in the last video, you'll notice one of them says that the integral of secant kx tangent kx dx is equal to 1 over k secant kx, right? Well, you notice in this case, k is 3, so and it's plus a constant, of course. So really, at this point, once you identify k, it's just a matter of plugging things in. This is going to be 1 over 3 secant 3x plus a constant, right? And that's the whole thing. So right now, there's not a lot of computation when it comes to that, other than using that power rule that you have to do a little computing on. Don't worry, we will get to the heavy computation, just not in this section. Okay, so these things are pretty straightforward. You can most of the time just use a formula and come up with it, right? And so you want to get used to these things as we go through them. Okay, now I want to talk a little bit about initial value problems. In calculus, we often call them IVPs, right? Just because initial value problems are so common, especially if you're doing any physical science. These things show up a lot. So this is an initial value problem. Wow. It's a good thing I teach math and not spelling. Okay, so an initial value problem. And it might look like this. And this is technically what these are called when they're presented to you in this form is a differential equation. Now, it really is just a derivative at this point, but we'll be told something like this. dy dx, right? So that's a first derivative, right, with respect to x. So it's the same thing as y prime is equal to 2x minus 7, and then we're given an initial value. Okay, so the initial value tells us that y of 2 is equal to 0. Okay, so let's go ahead and walk through this. And so we're going to be looking for the antiderivative with this initial value problem. With this initial value, we should be able to find the exact antiderivative of this thing. So I'm going to integrate 2x minus 7 dx. And let's see here. So let's see. The integral of x. Did I just say take the derivative? I meant to say take the integral if I said take the derivative just now. But anyways, if I'm going to take the integral of x, that's going to be x squared over 2. So I still have the 2 times that. You notice how I'm not separating all the steps this time. The integral of negative 7 is going to be negative 7x. And then on top of that, I have a plus c. Right? And notice here the 2's cancel out. And so this comes out to be x squared minus 7x plus c. Now, here's where the initial value comes in. Right? So I know from this that y is equal to x squared minus 7x plus c. But I also know that y of 2 is equal to 0. So that's my initial value, which means that y is 0 when x is 2. So that means 0 is equal to x squared minus 7 times x plus a constant. And if I simplify this, this is 4 minus 14, so 0 is equal to negative 10 plus c, or c equals 10. Right? And so now I actually know what the value is, and I can put the whole thing together. The antiderivative from this initial value problem, the solution, is the equation y is equal to x squared minus 7x plus 10. Right? And so it's just a matter of using that initial value to try to get a hold of c. And we can do this actually with our trig functions as well. Where'd I put it? There it is. So let's say I'm given ds dt, right? So this is s prime, or the derivative of s with respect to t, is equal to sine t minus cosine t. And we're given an initial value that s of pi is equal to 1. Okay, so that's my initial value. So what that means is I have to integrate sine t minus cosine t dt, right? So the integral sign is negative cosine. The integral of negative cosine is sine. And I need a constant, right? So I have plus c. So now I know what s is equal to. And as far as differential equations go, the solution to a differential equation is the function that you're looking for. So with differential equations, you're actually looking for a function that satisfies the equation. So looking at this now, if we throw in our initial value that s of pi is equal to 1, that means 1 is equal to negative cosine of pi plus sine of pi plus a constant. Well, cosine of pi is negative 1, right? You can just picture the cosine. So this is the negative of negative 1 plus, now sine of pi is 0. And so we have, well, that ends up being 1 plus 0 equals c, or excuse me, 1 plus 0 plus c is equal to 1. And just cleaning this up a little bit, I end up with 1 is equal to 1 plus c, and the only way that can be true is if c is equal to 0, right? So quite often the constant that you're looking for is a 0, which means that my function s is now equal to, well, I can reorder it so it looks a little nicer. Sine t minus cosine t, and it's plus 0, but I don't need to write that. And so this ends up being the solution to that particular equation. Okay, so we've seen that now, right? So what I want to do now is, okay, so